Title: Stubborn Perseverance: How Henry Ford Solved the Car Puzzle. Part 1 of 3. Problems, Significance, and Root Causes. Introduction. Henry Ford's story begins with stubborn perseverance. He kept trying while others gave up. Before his breakthroughs, building cars was slow, costly, and handcrafted. Part 1 explains the early problems he faced, why solving them mattered, and the deep causes that made mass production so hard. Part 1. Early Problems in Car Making. Early car makers worked like master craftsmen, fitting each part by hand. That meant every vehicle took a huge number of labor hours and could be different from the one before. Factories were crowded and poorly organized, parts arrived late or wrong, and workers had little training. The result was high prices, slow delivery, and uneven quality. Many consumers could not afford cars, so demand stayed limited even as interest grew. Part 2. Why solving the problem mattered. Making cars faster and cheaper changed how people lived. Affordable cars let families travel farther for work and school, opened suburbs, and created whole industries such as road building, gas stations, and motels. Faster production created steady factory jobs and helped the national economy grow. In short, solving car-making problems reshaped everyday life across the country. Part 3. Root causes that kept production hard. Several deep causes made early car making inefficient. First, the craft model. Skilled workers did many tasks, so scaling up meant finding many more skilled people. Second, parts were not standardized, so fitting often required custom work. Third, factory layouts were random, causing wasted walking and slow flow. Fourth, supply chains were fragmented and unreliable. Fifth, companies lacked simple metrics to find bottlenecks. Sixth, tooling and jigs were scarce, so many tasks stayed manual. Finally, limited capital meant firms could not afford big, well-designed plants. Part 4. The Human and Safety Dimensions. Workshops were often dangerous and exhausting. Poor lighting, heavy lifting, and repetitive motion caused injuries and fatigue. High turnover made training costly and reduced steady productivity. These human costs mattered because they limited how fast a factory could run and how reliably it could produce quality vehicles. Part 5. Early signs that change was needed. Shop managers saw wasted motion, long waits for parts, and stations that blocked the whole line. Dealers reported long wait times for deliveries. Customers complained about frequent repairs. Some firms tried to meet demand by adding overtime, but that increased errors and lowered morale. These signals showed the system was failing, not just a few workers. Part 6. Early attempted fixes that failed. Many early fixes patched symptoms instead of redesigning the system. Hiring more skilled workers was costly and unsustainable. Adding shifts and overtime raised output temporarily, but caused mistakes. End-of-line inspection found defects, but did not prevent them. Bigger buildings without workflow changes only amplified waste. Partial standardization helped a little, but left costly fitting. These attempts taught one lesson: small fixes cannot replace a new process design. Part 7. What comes next in this series? Part 2 will describe the breakthrough ideas Henry Ford and his engineers used to redesign production: task simplification, standard parts, moving lines, jigs, supplier coordination, and line balancing. Part 3 will show the wide effects, economic, social, and environmental, and close with practical lessons anyone can apply to solve big system problems. Breakthroughs, step-by-step model, and how Ford made it work. Introduction. Henry Ford's real advantage was not a single invention, but a set of simple, disciplined changes that worked together. Part 2 explains those breakthroughs and lays out a clear step-by-step model that turns slow, costly craft work into continuous high-volume production. Task simplification and focused repetition. Ford and his engineers watched each job carefully and broke it into tiny steps that any worker could learn quickly. Instead of asking one person to do many complex fits, each worker performed a short, repeatable motion. This reduced mistakes, cut training time, and let workers become very fast at their single task. Over time, small improvements at each station multiplied into big speed gains for the whole line. Standardized parts and interchangeable design. A key change was insisting that parts be made to exact measurements so they would fit without adjustment. Suppliers and in-house shops produced identical pieces, and engineers designed parts to common interfaces. When bolts, bearings, and panels were interchangeable, assembly became predictable. Repairs after purchase were easier too, which improved customer trust and lowered warranty costs. Moving the work, not the worker. Henry Ford turned an old idea into a factory revolution: move the car to the worker. Using conveyors and moving platforms, the vehicle passed steadily from station to station while workers stayed in place. This eliminated wasted walking and waiting, created a steady work rhythm, and made it easy to measure how long each task took. The result was a smooth flow that managers could speed up or slow down in a controlled way. Jigs, fixtures, and simple tools. To make fast work reliable, Ford used jigs and fixtures that held parts precisely where they needed to be. These tools prevented the wasteful trial and error of fitting and ensured consistent quality. Jigs did the positioning, so workers only needed to tighten, fasten, or check, actions that were quick and repeatable. Investing in simple fixtures paid off in faster assembly and fewer defects. Balancing workstations and bottleneck management. Engineers timed tasks and matched the number of workers to each station so no single point would slow the entire line. If one job took longer, they split it across multiple workers or redesigned the task. This balance kept the whole system moving and made production rates predictable. Managing bottlenecks became an everyday task rather than a crisis. Supplier coordination and delivery rhythm. Ford worked with suppliers to deliver parts on a reliable schedule. Instead of stockpiling large inventories, the factory expected certain parts at certain times. Early versions of just-in-time thinking reduced storage costs and highlighted supplier performance. When suppliers met rhythms and specs, the factory flow stayed steady. When they did not, managers fixed the contract or the process. Training workers on focused tasks and measure basic metrics daily. Because tasks were small and consistent, training became shorter and more effective. Managers tracked simple metrics, units per hour, downtime, defects, and used them to guide improvements. Ford paired higher pay with steady productive output so workers benefited when the line improved. That alignment of incentives helped reduce turnover and supported quality gains. Continuous improvement and experimental mindset. Ford encouraged small tests: tweak a tool, rearrange a workstation, or change a part size and measure the effect. Successful changes were standardized and shared across other lines. This steady experimentation kept the system evolving and allowed the plant to adopt new technologies and methods without major disruption. Step-by-step model you could apply anywhere. Begin by mapping every action in the current process and time each step. Simplify each job into repeatable motions. Standardize interfaces and parts so pieces are interchangeable. Design a flow so the product moves smoothly past workers. Provide jigs to remove fitting tasks. Balance workstations by timing tasks and reallocating labor to avoid slow points. Coordinate with suppliers to match delivery rhythms.
Train workers on focused tasks and measure basic metrics daily. Test small changes, adopt what works, and scale the improvements. How Ford managed the human side. Ford raised wages and offered stable shifts to attract reliable workers. He combined that with clearer expectations and predictable tasks. While monotony was real, higher pay and steady hours reduced turnover and made training investments worthwhile. Over time, unions, safety rules, and ergonomic improvements softened the harshest aspects of repetition. Early results and measurable gains. When Ford implemented these changes at scale, production time per car fell dramatically and output rose from small batches to thousands per week. Lower unit labor hours let Ford cut prices so more families could afford cars. The improved reliability reduced customer complaints and service costs. Those measurable gains proved that system design, not just harder work, generated value. Scaling and replication. Once the model worked, Ford duplicated the line in other plants and trained managers to copy the layout and rules. Because the system used standardized parts and tasks, new plants could start faster and with predictable results. The template approach turned local success into national industry transformation. Common pitfalls when applying the model. Avoid partial fixes. Changing only one element, adding a conveyor without standard parts, for example, often creates new problems. Do not forget the supplier side. A fast line needs fast, reliable supply. Watch worker morale. High repetition can harm people if not balanced by pay, breaks, or rotation, and avoid treating measurement as punishment. Use metrics to guide improvement, not to blame. Real-world example in plain terms. Imagine building a bicycle where one worker welds frames, another fits brakes, and a third paints. Now picture moving the frame down a line so each worker does only one quick action. With identical frames and exact brake mounts, the team builds many more bikes in the same time with fewer mistakes. That's the Ford idea in everyday language. What comes next in the final part? Part 3 will show the wide social and economic effects of the assembly line, discuss trade-offs and unintended consequences, and end with clear lessons you can use in school projects, teamwork, or future careers. The final part will connect Ford's methods to modern manufacturing, software, and service systems so you see how the same ideas still shape work today.